Welcome to our webinar 2D Mat, 2D Materials in Tribology, and today's talk by Professor Yury Gogotsi, Maxines, a decade of discovery and expansion of 2D materials. Before we start, we want to thank our sponsors for their support. We are sponsored by the two MDPI journals Coatings and Lubricants, as well as Frontiers in Mechanical Engineering and Artec Instruments.
Ladies and gentlemen, it's my great pleasure to welcome you all to the first webinar 2D Mat, which is an abbreviation for 2D materials in tribology. My name is Andreas Rosenkranz. I'm professor for material-oriented tribology, and together with my good friend and colleague Philip Ritzma from TU Vienna, we are organizing and hosting this new monthly based webinar series. Maybe Philip, you may want to say some words.
Yes, hi from Vienna, everybody, and welcome to 2D Mat. We are very much looking forward to starting this webinar series with Yury Gogotsi. I'm a postdoc at TU Vienna for tribology at Gachot Tribology Group. And thank you very much for joining us. And I'm very much looking forward to the talk by Professor Gogotsi.
Yes, our webinar is a monthly webinar, means that we're going to have every month for 1 year, roughly, some interesting talks about 2D materials and tribology. Today, the entire webinar is going to be kicked off by Professor Yury Gogotsi from Drexel University. We feel very honored that we have Yury as our first speaker. And our sponsors are MDPI journals like Lubricants and Coatings, also Frontiers of Mechanical Engineering. From the industrial side, we have Artec Instruments, a big manufacturer of tribological equipment. So thank you very much for the sponsors to help with the organization. And now I would like to take this opportunity. I'm very sure that you all know Yury Gogotsi very well, but I would like to take this opportunity anyway to say a few words about him. Yury is actually the head of the nanomaterials group at Drexel University, United States. His group is very well known and has a long-lasting reputation for the synthesis, characterization, and application of carbon nanomaterials, as well as Maxines, which are the new 2D metal, transition metal carbides and nitrides. Yury has published more than 900 peer-reviewed journal papers. He has reached an incredible age index of 180 with still a rising tendency. So very soon, I'm pretty sure that we will be able to celebrate an age index of 200. He holds more than 55 patents. He has received numerous awards recently and some time ago. For example, he is among the most cited and most influential researchers in material science, and he has received this award a couple of times. His presentation today is going to have the title Maxines, a decade of discovery and expansion of 2D materials. So we are very much looking forward to your presentation. And please, Yury, introduce the magic world of Maxines to us.
Andres, thank you very much for this kind introduction. Thanks to you and Philip for inviting me to be the first speaker. Today, I'm going to talk about this very large family of two-dimensional materials, still young, but growing very quickly. And I will dedicate the first half of my talk to description of Maxines, the synthesis, properties, particularly mechanical properties relevant to tribology. And then I will show you some examples of recent tribological studies, including those coming from Professor Rosenkranz's lab, also Vadim Chalin lab, and Aniruddha Sumas from Argo National Lab. While I used to work on tribology of carbon materials, particularly carbide-derived carbons, we cannot cover everything in Maxine world, and we don't have like our own current tribological activities at Drexel here. But let me start with Maxines. You have been looking at this picture already for a while, and you can certainly see these models of Maxine structures with red spheres representing transition metal like titanium, moly, vanadium, niobium. And black dots connecting them are carbons and nitrogens. So those are structures of typical two-dimensional carbides and nitrides that come in many flavors, many colors, many kinds, and they have an amazing variety of applications, which I'm going to cover today here. Of course, in the next 40 minutes of my talk or so, I won't be able to tell you everything about Maxines. However, this very recent review article, which we published in Science about 2 months ago, or maybe already 3 months ago, provides a pretty recent overview of activities here. However, as you will see among the applications mentioned here, energy storage, communications and electronics, shielding, biomedicine, sensor, optoelectronic, environmentals, there is nothing about tribology or mechanical, simply because the field of tribology of Maxines is very recent, just emerging here. But let me just make a step back and go to two-dimensional materials in general here. Maxines are a part of a large family. And of course, graphene and graphite as its precursor is the first one. Most studied, people pay most attention to it here. However, you can recognize among those materials a number of other materials widely used as solid lubricants, boronitride, transition metal dichalcogenides, such as moly disulfide here. So why are 2D materials of interest for tribology? A main reason is that they have weak bonding between 2D layers, which allows sharing and sliding of 2D layers relative to each other. Also, layered 2D materials can be dispersed in solutions, water, organic solvents, and applied to the surfaces as a liquid lubricant or form a continuous coating protecting the surface here with a good surface coverage, helping to create tribofilm, minimize interaction between the layers. And finally, also, it's possible to intercalate a variety of molecules between the layers, which again can control those interactions between the two-dimensional sheets, eventually decreasing the friction here. So what are Maxines? Maxines are carbides and nitrides of transition metals. The name actually came initially from their precursors, Max phases. My colleague at Drexel University, Professor Michel Barsoum, is the father of that field of layered carbides and nitrides. Of those metals, carbon nitrogen comes X, M stands for transition metal from this group. A is one of the elements of this group here. What we basically do to make Maxines, we remove a element from Max, what is left is MX. And as a result of this etching, oxygen, chlorine, fluorine, other elements are added to the surface. So TX stands for this surface terminations here. And these sheets produced have tunable surfaces, tunable interlayers, fast transport, ionic interaction, charge transfer in these materials, many other interesting characteristics. But what is also interesting, there also majority of the metallic have conducting form, but their surface looks like a surface of transition metal oxide, hydroxide, that can be easily dispersed in water here. And there are, of course, just a couple of atoms thin, so those are two-dimensional materials, in fact, here. Now, I already mentioned there are many of them available here. And what is also important here, that the number keeps growing. So we have choices. We're not limited. It's not just like you have a graphite or graphene or boron nitride. We have materials to choose from. And they come in a variety of different flavors. We call them like a M2X, M3X2, M4X3, M5X4 structures. What it simply means like a 4 layers of transition metals, say 3 layers of carbon. Moreover, we can make materials with an outer layer being one element, for example, molybdenum, and another one, middle layer, the blue one here, is titanium, for example. So known out-of-plane ordered Maxines. It's also possible to make Maxine with plane basically in plane ordering, where there are alternating atomic columns of different elements on the surface, or HEA one, and make a material with divergency. So basically atomic column missing on the surface. And it's also possible to mix element. We can make solid solution on M side, for example, mixed element, vanadium, titanium. Or we can also make material with a solid solution X side, carbonitride. And just a few months ago, a couple of papers were published on forming high entropy multi-elemental Maxine. So the key message is here is that we are really doing atomic engineering of materials. We can design structures with transition metals, carbon, nitrogen, and those surface terminations on the surface, which add another layer. If you look back at the table I showed to you and count just transition metals, carbon, nitrogen, take into account all this in-plane, out-of-plane order structures, you will easily end up with more than 100 of stoichiometric compositions possible. Multiply by 10 different surface terminations showed so far, and you will end up with more than 1,000 of stoichiometric compounds only. But look at the solid solution, high entropy, multi-element compositions. There is no limit to a number of Maxines that can be made here. And this is very important. We have an enormous family of materials with compositions that can be predicted, structures that can fit different applications. One of the interesting things to mention, Maxines are actually making also not like a more or less regular, very thin, few angstrom structures, but also the thickest known, a bit larger than 1 nanometer structure with 11 layers if you count surface terminations. And what it gives them actually a rigidity. They are much stiffer. The bending modulus, couple of magnitudes higher compared to thin materials, graphene. So they really behave like straight sheets on the surfaces here, at least the thickest one here. Now, we can make them by many different ways. Typically, we use etching. We remove an element by etching in sulfuric acid, hydrofluoric acid, by etching in salt acid solutions, and so on. And you can form this a variety of structures because we need to remove a layer bonded by strong chemical bond, A layer to M here, covalent or metal bond. So we cannot simply share them. We cannot simply use max phases as solid lubricants, unlike dichalcogenides or graphite would be used here. However, after we have etched it, either wet chemically or in emulsion salts, they all give different termination. For example, emulsion salt etching will give chlorine, bromine, other termination, halogens. Etching in aqueous solution will provide OH, fluorine, oxygen here. We get particles which are bonded by weak van der Waals bonds, just like in, say, clay or graphite. And we can delaminate in single layer flakes here. And this is an example of emulsion salt etched material when there are chlorine atoms on the surface now between the layers here. What is very important? I just praised the number of Maxines can be made. There are actually already more than 200 two-dimensional materials reported. However, how many of them can be produced in amounts that would make their, for example, tribological or structural applications feasible? Just a couple. Those are probably graphite, graphene, boron nitride, moly disulfide, tungsten disulfide, clay, couple of oxides. All other materials are made in tiny amounts, often by CVD or PVD deposition in high vacuum here. Maxine, all these materials can be made in a scalable way because we take a ceramic powder, we put it in a reactor, we etch it, we produce Maxine, which can be after that processed into film, layers, whichever way you make here. So this is how we start. We start with this ceramic powder, max phases. Hexagonal particle of typical max phase. These three bright layers of atoms are titanium atom in this case. Layer connecting them in this particular example is aluminum, titanium 3 aluminum C2. We etch it in an acid. You can see particle changes become looking like very much like a thermally expanded graphite. And aluminum is gone, but you may notice surface terminations that appear on the surfaces here, less bright atoms terminating surface. And when we separate them in a flake, this is a single layer flake of titanium 3C2. TX stands again for surface termination here. And you can see it's electronically transparent. It's just about 1 nanometer in thickness. And you can also see well-ordered crystalline structure. So the remaining strong crystalline materials. Typically, we treat them dispersed in water, but it's possible also to dissolve them in polar aprotic or protic solvent. For dispersion in non-polar solvents, we will have to do surface modification of this material. That's possible. This is doable if needed, for example, for dispersion in oil, but it won't happen by default intrinsically because surfaces are polarized. But what is also important that we can use just aqueous solution and not really like an aqueous. It's a really pure water, no surfactants, no binder is needed, no toxic compounds added. And we can print them, we can make fill, for example, a fountain pen, roller ball, and write with Maxine. We can produce coating by spin coating, spray coating, interfacial assembly, basically by every single method possible. And I won't bore you with going into details because you can process it like any other colloidal particles in solution. We can separate them by sizes, for example, by centrifugation and so on here. But what may be also important for those of you interested in lubrication, tribology, coating is that above a certain concentration, these materials form liquid crystal. For example, for large particles, it's already happened at about 13, say, over 10 milligram per milliliter. Smaller particles will require larger concentration, but if you go even to a bit higher concentration, for example, 26 milligram per milliliter, you can form a nematic phase. So basically, even in the liquid, all these particles align relative to each other. They cannot rotate freely anymore. And as a result, we get ordered particles, which again can be used to produce uniform coating on the surface. Another important factor in application of materials in tribology and many others is stability, environmental stability, chemical stability. And we have been recently pushing really the envelope in increasing stability of these materials, which are thermodynamically less stable than, say, graphite or graphene. And we showed that we can keep stoichiometric, well-prepared titanium carbide Maxine, and this is most common one, the first discovered, most studied titanium 3C2 in solution for months. Raman spectra show no change after 6 months storage in dilute solution. And even after 10 months of storage, you can see just a couple of pinholes. I circled them here in red because otherwise you won't even notice it here. So what are the properties? Actually, most of application of Maxines to date benefited from its high metallic electrical conductivity. So energy storage, printed electronics, electrodes, shielding, antennas, and so on here. However, for applications we're talking about today here, what is important is that Maxines are strong and stiff. They inherited their mechanical properties from strong lattices of cubic transition metal carbides. For example, titanium carbide, bulk titanium carbide is widely used for cutting tools, just like tungsten carbide. And you can look at the layer of Maxine, and you can see again here a single flake on an aluminum oxide substrate, probably about 20 micron in size, and a few flakes on TM grid. You can look at them as like a 1-1-1 cut of the cubic sodium chloride carbide lattice of conventional transition metal carbides or nitrides, like titanium carbide, titanium nitride, TiC, TiN. And they are again crystalline single crystals. And I mentioned already their stiffness. For example, graphene would not hang in a hole of TM grid this way. It would collapse because it's very flimsy. Maxines with several layers of transition metal are significantly stiffer here. But you can also make a thick film. For example, this is a couple of micron film. It means that there are more than 1,000 monolayers are in this film. Again, very similar to graphene here. And they are dispersible in water because they're hydrophilic, have this oxide surfaces here. And again, what is important is wide control over properties. If you look at mechanical properties predicted for these materials, you will see young modulus being in hundreds of GPa. It's a little bit lower than in-plane modulus of graphene, which reaches a terapascal or diamond. However, it's extremely high. Moreover, as I mentioned, it's also stiffness, which is higher. Bending rigidity is significantly higher for those material things here. And it's definitely high elastic constant compared to, say, the chalcogenides here. And again, we can control those properties. We can control them by number of transition metal, type of transition metal, carbon or nitrogen. We can control them by surface terminations here. And all properties will change with this here, from optical properties, absorption, to work function, to band structure. It means conductivity, metal semiconductors here. Andreas was very kind to provide several slides to me from his research. And as you can see, this is an example, for example, of stiffness and moduli changing for M to C structures. Those are the thinnest of Maxines available as a function of surface termination. So whether we put oxygen, OH, fluorine, chlorine, those properties change. So again, we have a tunable family of materials. You may design material with properties that you need for applications here. Select transition metal, change surface termination, get the material here. A couple of years ago, together with Dr. Vadim Borysyuk from Sumy State University, who was a visiting scientist at Jacksonville at that time, we conducted molecular dynamic simulation of mechanical properties of Maxine, dynamic of the fracture. And you can see they actually can sustain significant strain up to 10% and show predicted very high also stress to failure, which goes to, again, 20, 30, close to 30 gigapascal, depending on type of Maxine, number of layers here. And experiments actually largely confirmed this. Those are mechanical tests conducted in collaboration with Professor Sinitsky from University of Nebraska-Lincoln, showing that Maxine single layer, double layer flakes have actually very high moduli. He tested number of materials. And what is important, when it bakes, there is no catastrophic failure. You see, this is a suspended film of Maxine over a hole in a silicon support. And you can see this small tip going through the membrane. The membrane doesn't fail. Graphene membrane would explode when it happens here. So it means also this gaseous failure, which is important. And while Maxine doesn't reach the same properties of graphene, but it's still very, very strong. And if you look at its modulus, classic modulus, it's higher than moduli of any solution processed material. So when we talk about graphene, we're talking about ideal crystal of graphene, separated from a perfect single crystal. And this one has a high modulus. But if you take graphene from graphite, reducing graphene oxide solution processes, mechanically share it, it will already have lower properties compared to titanium-32 Maxine. And we worked with colleagues to do further simulation of deformation and failure of Maxine sheets, confirming actually what we observed experimentally, that in fact, indeed, there is a gaseous failure of these materials without catastrophic cracking. So what it also means that these flakes are difficult to damage. They won't like a break well to each other, what happens, say, to carbon nanomaterials in dry environments here. They keep their protecting layer terminating the surface. They don't fail easily here. And that's actually one of the properties that contributed to these diverse applications. But again, let me stress, among all those applications we reviewed recently, there was no tribology, just because really papers on tribological application of Maxine started appeared when we already like finished these reviews here. And if you looked at the analysis done again by Andreas and Babak Nasuri, my former postdoctoral research assistant professor in my group, who is currently a professor at University of Indiana, Purdue, University of Purdue, Indiana, IUPUI here, you will find that all the mechanical tribological application actually make less than 5% of all the work. And primarily those are really mechanical application, composites, paper on mechanical properties of Maxine. So this is truly an emerging field of tribological applications of Maxines here. And you see there are just like compared to about 3,000 papers on Maxines expected in 2021 to be published here. And there were more than 1,500 published in 2020. You see, very small percentage comes on those materials. And again, mostly those were composites. And there are like about 20 papers on Maxine films and flakes here. And if you look at tribology, so on lubricants, there are just a couple of papers published here. So you realize how new is still the entire field here. And there are many limitations for solid lubricants. And of course, I don't probably need to talk to the tribology community about importance of liquid solid lubrication. Both of them have pros and cons, but there are many applications where liquid lubricants cannot be used, ranging from space to food industry, things here. And traditionally, of course, carbon-based materials, transition metal dichalcogenides, boron nitrides are the ones that have been used here. However, Maxines have their unique advantages here. It's not only the strengths, mechanical properties I mentioned, and actually, just to add to this, niobium carbide Maxine is even stronger, showed itself than titanium-32. And if we make the materials more perfect, minimize the number of point defects, vacancies on the surface and others, we can push values of their moduli to the predicted values that I showed to you in the table here, but also their surface chemistries. When you look at these Maxine flakes, they always have intercalated water layers in between, or you can replace water with organic solvents. You can replace water with other molecules, or you can also add ions here. And all these molecules will, on one hand, control interaction. On the other hand, those are quite strong, for example, hydrogen bond between oxygen OH terminated surfaces and this water. And even if you place it in vacuum, the water won't disappear by itself here. So years ago, we showed if you take carbide-derived carbons with extremely small pore size, and there is always some molecules adsorbed in pores that allow dry friction without failure, because it will be released on the surface, providing like a self-lubricating film. We believe similar behavior is possible in the case of Maxines here. And actually, work done by Andreas and his team and his collaborators showed that, in fact, solid lubricants like Maxines show very promising properties here. Those are pictures of the particles of multi-layer Maxine, not delaminated and exfoliated. But these layers are separated by very thin intercalated layers, or just have functional group on the surface. And this is actually very important, because keep in mind that, say, you can take two layers of graphene, bring them together, and form graphite, or multiple layers. There is nothing separating them, nothing preventing them to reconnect back into graphite lattice if they rotate in the right way. In case of Maxine, there is always a layer of oxygen or chlorine or fluorine on the surface. So if you bring them together, they will not form at a bulk titanium carbide particles. They will always stay separated. So they won't be able to stick to each other when you do it. So when they deposited 100 nanometer films on the surface of substrate steel and tested, what they observed in tribology here, that Maxine coating is actually drastically decrease the friction coefficient to about 0.1, which is very well compared, I would say, with carbon materials here. And actually, it cycled well over a long period of time. You can see 100,000 cycles. There are some spikes appearing, probably coating starting to wear off, but it still works here. So it means that it's possible to get a very significant improvement in the friction coefficient here. And the reason is potentially because Maxine flakes cover basically surface of the materials. They cover the surface of the counter body, making this tribal layer transfer, and they share it here. And actually, this was really an amazing result obtained in normalized VR life, greatly outperforming all other materials, including actually earlier tested titanium carbide Maxines here, in, first of all, VR life here, with also quite a low friction coefficient for this material here. So it basically means that Maxine can outperform solid lubricants here. But again, keep in mind, there is no reason to believe that titanium 3C2 produced by this method is the best Maxine. Even for titanium 3C2, you can have a variety of different surface terminations, more fluorine, more oxygen, more OH, chlorine, which allow you to control the properties further. However, there are also at least 30 already reported transition metal carbides and nitrides and carbonitrides. And as we discussed earlier, virtually unlimited number of others possible, and already a couple of dozens of solid solutions have been reported in addition to those stoichiometric ones here. Let me also show a couple of slides from another study, just to give example of another interesting property observed here. This is work done by Aniruddha Sumant at Argo National Lab and Professor Vadim Achalin, also a former colleague, former research assistant professor in my group, who is currently associate professor at Missouri Tech here. They tested titanium-32 Maxine films, along with graphene and in comparison to graphene film in controlled environment, in dry environment using ball and disc turbometer against diamond-like carbon coated steel balls. Diamond-like carbon is known for its very, very low friction coefficient, also eventually showing super lubricity. It means that extremely small friction coefficient. And what they found that actually titanium-32 shows under these conditions friction coefficient that goes another order of magnitude below what I showed to you in the previous study to 0.01, which means basically super lubricity here. And while at a certain point there is a sharp increase and breakthrough, if also graphene added to it here, probably prevent from Maxine films, larger graphene flakes may kind of stabilize, coat them, shield them here. There is basically continuous super lubricious behavior over a very large number of cycles here. So this combination actually appeared to give even better properties compared to pure titanium-32 and significant improvement compared to say graphene or just a surface, uncoated surface of silicon here, with also much smaller wear scar and excellent performance here. So I think those are just a couple of examples here, demonstrating that Maxines have a potential in tribological applications here. It can be very low wear coatings. It can be coatings working in dry environment like dry nitrogen, and potentially many others. I've seen work demonstrating that actually Maxine can work under extreme pressures applied. So when there is a very heavy loading of the contact here. And of course, this is still the beginning of the road. Just because, as we talk today, there are a variety of Maxines. Just their varying method of synthesis allows to produce different surface terminations, different chemistries, even for the same Maxine. Titanium-32 we discussed today is actually a very good Maxine because titanium and carbon are both very abundant elements here. But you can say the same about titanium-2C or titanium-3C and carbon nitride or titanium nitride. And there is a good probability that some others Maxine with, say, moly or vanadium may appear to be even better lubricants. But we can also explore this variety of surface termination, surface functionalities, which further allows us to control interaction between two-dimensional sheets. So again, controlling chemistry, controlling healing or introducing defects can give further improvement in properties and also match those films to specific surfaces, to specific operation conditions here. So finally, we can also control thickness of flakes. We can control degree of delamination. We can control transition metals here, leading to tunable mechanical properties, tunable lubrication properties here. And of course, lateral flake size can be added also to the set of parameters which may allow us to control those properties here. So I think this is an emerging application for Maxines, where tremendous amount of work must be done, both probably predictive computational to guide selection of specific Maxine, better understand of mechanisms of lubrication and ways to control friction with the help of Maxine. Also better understand interaction with different surfaces, substrates, to select right Maxine for the right couple, whether we're talking about steel or ceramic surfaces or anything else here. But there are opportunities And those opportunities should be explored, of course, by the tribology community, because material scientists, materials chemists like myself have been developing many different Maxines so far, and it would be exciting to see those applications. Before I finish, and also for people who might have joined us a bit later, I just wanted to show another slide from our recent editorial published with Qin Huang in the April issue of ACS Nano. It actually accompanies a virtual issue on Maxine, showing that we have all these transition metals to select from: carbon and nitrogen, or a mix of those, and all the surface termination, which come in a variety of structures. Moreover, we can even change separately layers to achieve additional properties and surface terminations. So predict, select, test, screen, and explore applications of those materials in tribologies, and we may get a new family of solid lubricants, or also maybe modifying additives to liquid lubricants to achieve improved properties in the case of liquid lubrication as well here. Also, what I wanted to mention is that Maxines are step by step moving from university laboratories to industry and to practical applications. And earlier this year in April, a Maxine association was created by Terence Barkan, the same who created the Graphene association here. And if you are interested in applications, updates on patents, industry news, new breakthroughs in research, you are welcome to go to maxines.org website, and you can join the Maxine Association and also get connected to material suppliers, potential end users, and of course to the research community as well here. There are many other applications, of course, going beyond tribology. There are many challenges we're still facing, improving, making new Maxines. Of all the predicted, probably about 50 different compositions have been reported, maybe a little bit more. Achieving control over termination structure here. You probably don't need bare Maxine for tribology, but of course they're interesting for physics study of the properties here. Many other techniques are being explored, and also particularly I would like to stress assembly of hybrid materials with 2D structures. For example, graphene Maxine mix in the work done by Aniruddha Sumant and Vadim Achalin showed a better performance compared to pure graphene or pure Maxine. And of course, similar way, hybridization with boron nitride, molybdenum, other materials is possible here. And of course, Maxines are also particularly beneficial in various types of conformal technologies and fields here. And this is my very last slide. I wanted to leave sometimes time for questions here. Of course, the work on Maxine synthesis that I showed today was done by my research group, my students and postdocs. This is an outing when COVID let us finally get together with a number of friends, colleagues, and have our group gathering in backyard of my house, have some fun together. So those are people who really did the work, who conducted synthesis, studied properties of Maxine. We collaborate with a very large number of people around the world in many different countries, many different places, because there are so many applications for Maxine. We are learning constantly about their properties, about their applications. And I'm personally very much excited about opportunities for Maxine in tribology. And thank you very much for listening to my talk. If you want to learn more about Maxine, I also invite you to visit our website. We have plenty of information. You can download our paper. Password for PDF file is NMG, all small letters, stands for Nanomaterials Group. You will find videos, you will find beautiful pictures of Maxines and a lot of relevant information on the subject. With this, I'm going to stop. Thank you very much. I will be glad to take questions.
Yeah, thank you very much, Yury, for this inspiring talk and for the very broad overview. Actually, the people are already using the opportunity to ask the first questions via the chat. So either way is welcome. You can ask via the chat. You also can try to ask personally. And together with Phil, we will organize a little bit the ongoing discussion. So maybe I'm gonna give you the first question that appeared in the chat. So the first question is, can we control the pore size of Maxines?
Well, usually Maxines flakes, if not overage, don't have pores. However, it is possible to make more aggressive removal of atoms of transition in the layer leads to pores. So we made porous Maxine membranes, and yes, by changing the synthesis condition, you can control the pore size.
Excellent.
Okay, thanks. Yeah, big thanks also, Yury, from my side for the very inspiring talk. I will give the next question to you from the chat, which is how we can determine the number of layers in Maxine and how can we synthesize few layered Maxine?
Well, you can determine the number of layers in Maxine by atomic force microscopy, in TM by changes in the beam intensity going through. And actually, when you have some experience, you can just simply drop Maxine colloidal solution on a wafer, silicon wafer with oxide layer on the surface, just like graphene, and you will be able to distinguish between single and few layers flakes. So this is like an express method. Unlike graphene, for example, Raman spectroscopy does not show difference whether you have single or few layer flakes because there is less coupling between the layers, as I tried to explain. And yes, you can make few layer flakes just by delaminating multi-layer particles produced after etching.
Right.
Thanks.
The next question goes, how to check about the purity of the synthesized Maxines?
Good question. Well, usually we first look at X-ray diffraction to see if there are leftovers from say, max phase precursor, or sometimes max phase precursor contains, say, cubic particles of impurity of carbide. And of course, imagine you use it as lubricant and you have hard a couple of microns particles of titanium carbide there. Definitely it's going to do a lot of damage here. But after delamination, those are always gone. Typical impurities can be salts from etching, for example, aluminum fluoride. And again, if you have large amount, you can see it in XRD. If this is a small amount, you can do EDS analysis, for example, microscope, and look for aluminum leftovers or other elements. Yeah.
Very much.
Okay, then there's a question which we already had, basically. So the next one would be, can we integrate multiferroics ferrites with Maxine for better pseudo-capacitance behavior and magnetic ferrites for super electromagnetic wave absorption behaviors?
Well, it goes, of course, a little bit away from lubrication tribology, but a short answer is yes. You can look at Maxine just like a two-dimensional sheets of thin material, just like a graphene. Anything you can do, say, with graphene or graphene oxide or molybdenum, you can do with Maxine. You can mix it with multiferroics, you can mix it with iron oxide particles, and after that, by spray coating or vacuum-assisted filtration, produce film. So in general, it means that hybridization can be done not only with other two-dimensional materials. You can also hybridize Maxine with other zero-dimensional and one-dimensional, like carbon nanotubes or diamond nanoparticles, for example, which are also widely used in tribology.
Excellent. The next question also quite interesting. What about the cost in comparison to graphene? the fabrication cost, I believe.
What is the cost of graphene? Let me ask you. It's a difficult question to answer because initially, first, Maxine is still produced in small amounts. It means that like any new material, they are relatively expensive. However, what you need to look at is a fabrication method and also elements that form Maxine. So when you have, for example, gold or platinum or tellurides, you have elements which are rare. It means whatever you do to it will always remain expensive. When you have earth-abundant elements, it means that economy of scale always works. We improve methods of synthesis, we decrease the cost, improve the volume, decrease the cost. And this also holds for many other materials like graphite. For example, if you take a graphene monolayer growing by CVD, you will end up with enormous cost. It will be like for monolayer, it will be tens of dollars per square centimeter. Recalculate into kilograms, and it will be astronomical price here. Take graphene produced by sharing natural graphite, and this is a different ball game here. So I think what we need to initially find out are there technological advantages in using it, because based on elemental composition of this material, there is definitely a way to produce them in large quantities at moderate price.
Thank you. A related question to this also, I will jump one, is will the cost of battery or supercapacitor reduce if we use Maxines?
Well, again, if you talk about different application, electrochemical, the same situation is here. It will be reduced if use of Maxine allows you, for example, to have half of the battery size. Or it may remain the same, but your battery will be charged, for example, with half of the time required by conventional battery here. So I think we really need to talk in terms of performance here. We pay more for something that gives us better performance. Or again, if device becomes smaller, if say Maxine lubricant is more expensive, but you lubricate once and after that machinery can operate, say, for a month without further lubrication addition, it will be less expensive compared to something which is 10 times less expensive, but requires lubrication on daily basis, on hourly basis, additional one here. So I think this is this type of approach you need to think. There is no like a simple answer, okay, kilogram of this costs less than kilogram of that, so it's more expensive. It's really determined by improvement to performance, whether it's a battery or a lubricated bearing.
Yeah, absolutely right.
Sure.
The Raman question Yury has already answered, honestly. Then we have a question, how to determine the best degas temperature for BET analysis of Maxine?
There is no best temperatures, no a really good way to do it. Let me explain why. Main reason is because you always have this intercoolant between the layers. So you can calculate theoretical specific surface area of Maxine, but there is no way for nitrogen or argon or any other gas to get between this layer of Maxine. So what you will be measuring? You'll be measuring the outer surface of the flakes. And you can do it with nitrogen. You can do it with argon. You can do it with CO2. But you'll always get only this outer surface. Unless you have completely exfoliated flakes and you make an aerogel in which you just measure the surface. So it's only outer surface. So it means that it doesn't matter. Unlike, say, porous carbon, you cannot get this information for Maxine with BET. So BET is unfortunately much less useful for analysis of Maxines.
Yeah. Thank you very much.
All right. Question related to the mechanical properties. Can we mix Maxine into polymers matrix to improve mechanical and electrical properties of polymers?
Yes, a short answer, yes, this has been done. There are numerous papers. The first one we published in 2014, but since that, there are probably a couple of hundreds of papers at least. Yes, you can also include mechanical properties. I think the statistical analysis, which wherever the slide is I showed to you here, shows you see Maxine composite materials. So those are exactly type of papers. There are probably many more actually, because many of them are for functional applications, composites, not for mechanical applications done. But yes, because of the stiffness. Moreover, let me also mention something. Because Maxine has a surface termination and a couple of layers thick, you can actually even covalently bond polymers to this material without losing its mechanical strength and conductivity, unlike, say, graphene, when it's not only very difficult to bond anything to the surface, but, for example, forming graphene oxide kills completely conductivity of the material.
Right. Next question, is there a relationship between number of layers and capacitance of Maxines?
Well, again, I understand. It's not surprising there are so many questions about energy storage, because at the moment, like about 1/4, if not 1/3 of all the publication research in Maxine is done on electrochemical applications. It depends. If you completely exfoliate material, open the structure, then again, ions can access all the surface, as we discussed with gas molecules. When Maxine flakes are stacked, there may be impossible for some of the ions, larger ions, for example, or ions solvated with solvent to access space in between. So there is a dependence, but it's not like a simple dependence that I can tell you, this is better or that is better. Lithium ions, protons can go even between the layers of stacked Maxine structure, but say large organic ion won't be able to do it.
Very good. Another question regarding the 3D architectures. Just like 2D or 3D material graphene, can we obtain the different shapes of Maxine layers by using some surfactants or chemicals?
Yes, with the only difference, you don't need surfactants or chemicals. But yes, it's possible. I, again, didn't talk about today, but you can treat Maxine just like many other materials. Unlike graphene, you don't need surfactants because it will be dispersed in water or also many solvents here. So you can do, for example, freeze drying, and you will produce an aerogel. You can incorporate it inside hydrogen polymer matrices. From liquid crystalline materials that I showed you before, we can even draw pure Maxine fibers. And actually, this is what cover of ACS Central Science for this work was published. It shows here. So yes, it's possible to produce 3D architectures by a variety of different ways. And certainly it is done, for example, for the same electrodes of battery supercapacitors or for functional textiles or many other applications.
I'm going to jump to a question which is really related to tribology, or at least to lubrication. There's a question, how stable are Maxines when dispersed in oil for lubrication? Which also relates to the surface termination topic.
Look, I would say that they will be very stable chemically, because if they can stay for a long time, even water, it was shown before in inorganic solvents like isopropyl alcohol or propylene carbonate, they can basically stay for years with no changes. So the same will be true for oil. But again, let me mention something that I stated maybe very briefly before. Maxines have polar surfaces. What does it mean? If you want to disperse them in non-polar solvents, like, for example, oils, hydrocarbons, aliphatic, aromatic, you will need to do surface modification that they can be done. But in this case, yes, you can form stable colloids, and has been demonstrated.
Very good. Yeah, I'm also jumping to a question which is related to tribology and lubricants. what makes Maxines more environmentally friendly than other solid lubricants?
I did not make this claim first. Second, I think carbon, for example, is sufficiently environmentally friendly. So if you talk about graphene, I don't see really problems with this. Molybdenum is also not awful here. But if you take, for example, titanium 3C2, which is like, again, most studied one we may discuss today. If it degrades in the environment, it produces titanium dioxide particles, which are very, very common, present a lot in nature. You eat it when you eat donuts in sugar powder, and carbon dioxide, methane, depending on the conditions here, carbon monoxide here. So there are no toxic residue formed by this. Also, Maxine has been studied in both human in terms of cytotoxicity, and at least titanium 3C2 and a whole bunch of other Maxines, actually, tantalum carbide, niobium carbide, have been shown not to be toxic. Also, zebrafish studies have been done in terms of Maxine release to aqueous environments, showing again there is no damage here. So I would say it's a quite environmentally friendly material. At the same time, I would not make a claim that it's say more environmentally friendly than carbon.
Right.
Yeah, of course.
Another question, at least related to tribology, one person asked, what about the thermal stability of Maxines, and which Maxine may have the best thermal stability?
This again a very good question, something I didn't discuss today. In vacuum, Maxines are usually stable to about 600-800 degrees C. At least some of them can go above that. They will start transform into conventional cubic carbide structures or other carbide structures at high temperatures. In air, they're typically stable to temperatures between 200 to 400 degrees C. My feeling is for most tribological applications, that's probably sufficient temperature. They only start losing water or adsorbed molecules at this temperatures. At high temperature, their oxidation starts, but again, it depends on the Maxine strongly. And rule of thumb, I would say, is that thinner Maxines less stable compared to thicker Maxines. So say niobium 4C3 will be more stable than niobium 2C. Titanium 3C2 will be more stable than titanium 2C thermally. But also defects, surface terminations, flake size contribute to their stability.
Okay, thank you. Yury, we have still several more questions. I don't know if you want to answer more or if you
maybe another one or two questions. And I would suggest after that, the rest, feel free to email me here. Here is my email address and our website where you can find a lot of information. So feel free to email, and I will be glad to answer further questions here. So maybe let's take another two questions before we wrap up.
Okay, here comes the last before the last. How to tune the vertical alignment in liquid crystalline Maxine?
Well, again, what you need to do, you need to first get liquid crystalline, pneumatic liquid crystal, the flake are aligned. When you extrude them, or for example, use doctor blading, they will align parallel to the surface. But then, you know, like your hair, you can basically brush them in opposite direction and they will stand up here. Yeah. So again, it's not something special for Maxines. You can use the same technique people used for liquid crystals in general.
Okay.
Okay, so maybe to close the discussion, maybe a question with a different background, which is also very interesting, I believe, because there's one person asking about biomedical applications and about the biocompatibility of Maxines. Can you comment on that?
Yes. There is a very significant interest to biomedical application of Maxines. We actually have at the moment 3 different funded programs in my group going on, ranging from dialysis to epidermal and implantable electrodes. And titanium 3C2, niobium tantalum carbide Maxines have been shown to be biocompatible. They are being explored for implants and also, of course, for epidermal electrodes and other medical applications, from drug carriers to photothermal therapy treating cancer. But you can also build a bridge to tribology here because, of course, hip joints, for example, all this moving part here, friction plays a very large role. Titanium metal is a very common implant material or titanium alloys. And if Maxines on the surface can, for example, improve tribological long-term performance of implants, and maybe also you can imagine adsorbing antibiotics molecules to prevent, for example, rejection by film formation. It may be a potentially interesting application for Maxine. I have not seen anything done in that area here. So you can marry tribology and biomaterials medicine in that kind of applications here. So I think it was a good question to complete here, because many properties that are important for one field are also important for other fields here. And that's where people in different fields should talk to each other.
Maybe in a couple of months, maybe in a couple of months after this webinar, we will see the first paper popping up.
Well, one of my goals is to encourage research on Maxines. We're not hiding, we're trying to be very open, because as you see, the field is enormous. So many materials, so many compositions, so many potential applications. No one can explore it alone. And this field really requires more people, more efforts. And of course, people who are expert in certain fields can do this job much better than us. And that's why I think it's so exciting here. With materials being available now, it's certainly time to explore applications, explore where these materials can perform better than other materials and solve problems that we have not been able to solve with other materials here, whether it's energy, medicine, tribology, any other field. And again, thank you very much to everyone for listening. Thank you guys for organizing this seminar series. I look forward to listening to interesting seminars in the future myself.
Thank you very much, Yury, for the inspiring talk, also for sharing your philosophy. I think this is the right way to push the overall topic forward. And thank you very much. It was an honor to have you today kicking off our webinar.
My pleasure. Have a great day, everyone, and goodbye now.
Take care.
Thanks, everyone, for listening. Thanks, Yury, for the great talk, and see you soon. We also invite you to submit your research to 3 current special issues in coatings, lubricants, or frontiers in mechanical engineering. You can find the links to the special issues in the comment section below the video.
Introducing the most advanced universal tribometer, the MFT 5000. With a modular architecture platform design, it is a robust surface testing instrument engineered to evaluate friction, wear, mechanical properties of materials, as well as lubricants over time. The MFT 5000's open XYZ stages and wide range of interchangeable modules and sensors allows users to self-implement and add-on customization and combine several tribology tools all on one device. These diverse modules accomplish various motions for any application and are capable of speeds from 10,000 RPM to 500 Hz oscillation. The complement sensors achieve millinewton to 12,000 Newton wide force range, with options of strain gauge, piezo, and capacitive multi-dimension force sensors. The Lambda Profilometer, combined with a patented inline design, coincide to analyze any surface, including glass, with ease. Because of its unique four imaging modes, the profilometer produces 3D information by creating sub-nanometer surface images automatically. A fully automated and simple software interface integrates the data, enabling researchers to design and conduct tests at nano, micro, and macro levels. To simulate real-life scenarios, the tribometer comes with several environmental control options that allows testing -120 to 1200 degrees Celsius temperatures. These interchangeable chambers are skilled in evaluating high pressure, vacuum, humidity, salt spray, and tribocorrosion conditions. Due to its multiple possible configurations, the MFT 5000 is used extensively across a wide range of industries, including oil, biomedical, semiconductor, coatings, automotive, electronics, materials, aerospace, and many more. On this platform, all types of tribology tests are possible. Our tech instruments, leading innovation in tribology and surface test instrumentation.